Very well, we will continue with our training, and from now on we will talk about fans or forcers. In inverter technology, we will no longer find only AC fans, like the one we have in hand, but we will also find triphase fans or forcers. To summarize, we could say that we will find three different types of forcers. These are AC forcers, which is the one we have been finding in any air conditioner so far and which are also found in inverter technology. We will also find DC and U, V, W forcers, these two being of the same operating mode, only a little different in the way of making them work from the board, but they are exactly the same. They are fans or forcers whose winding is three-phase, just like the compressor motor. Very well, let's start then by talking about the simplest one, which is the AC forcer, which is the one I have in my hand and I will show you right now. This type of fan has an AC power supply. What does this mean? That we will be directly feeding it with 220 volts or 110 or 127. A small phase shift capacitor will be placed. We had already been talking about this when we talked about how an AC motor works. It will have a rotation frequency of 50 or 60 Hz. The manufacturer already made the coils so that with a certain frequency of electron circulation the motor can rotate and function properly. So, it will always work according to the voltage we have on the line and the electricity. The board will only do is somehow send it that voltage. But the voltage of this motor from the board is not sent only through a contact relay, as the fans were previously powered. Now we don't have it. These relays are for working in fans with multiple windings that make them rotate at different speeds. But in the case of these fans, if we glued it with a relay, it would always rotate at maximum speed. So, we need some kind of circuit to be able to make it vary the speed. We are talking about the indoor fan, How is this change in rotation going to be produced? Let's keep in mind or think first of some parameters. What can we not do to vary the speed of this fan? Something we can't do is vary the voltage or frequency. So there we already have two things we can't vary. Because the voltage is already pre-established, that fan, at least the one we just showed, is 220 and the frequency is 50 Hz. If we vary the frequency, it will consume more electricity because the electron circulation will be confused with the rotation. And if we vary the voltage, the same. That winding will demand more electron flow due to the lower voltage and the amperage will rise, and with that the heat of the motor. So, since we can't vary these two data, how would we do the speed in a fan of this type? Well, this is produced through a circuit. The circuit that is used for this is this one that we see here on the board, which is obviously near the area where the fan is connected. This circuit is composed of some resistance, some filter capacitor, a triac and an optocoupler, as well as two power resistors. Optocoupler and triac are the main components. These two can be combined to form an optotriac, which would fulfill the same function. Now we will explain in detail each of those components. Don't worry. Well, what function do these components perform and how do they vary the speed without modifying either the voltage or the frequency? Let's understand it without any inconvenience. We have a frequency that we cannot vary, neither the voltage nor the frequency. What is that triac going to do? That triac, which is like a kind of electron switch, that triac has a power supply at this point. It was going to let the electrons pass from one side to the other, and also from one side to the other, depending on the moment in which it is powered here. When a voltage is injected at this point on this surface, the electrons are allowed to pass to one side and to the other. That is a triac. Unlike a transistor, which only allows passage to one side. We will see more about that later. So, when does it activate and deactivate? This is where the board needs the zero crossing detection. At this point, the microprocessor needs to know at what moments in time we cross zero. And that is where the importance of zero crossing detection comes in. These waves are symmetrical in the same way, but well, here it comes out a little more open. Don't pay attention to that. Why do we need zero crossing detection then? What the board is going to do is that, when the zero crossing is detected, the application of voltage to the triac is cut off. So, no voltage will be passed to the fan. It will wait for some milliseconds to pass, and then it will activate it. Then yes, voltage will pass from this point to the fan. All the power of that piece of the wave will be applied to the fan. When it crosses zero, the triac will deactivate again and will wait again for a certain amount of milliseconds that we will say are 3 milliseconds. 3 milliseconds are waited and then the voltage is injected and all this electron power is injected to the fan. When it crosses zero again, the same thing happens again. The power is cut off. 3 milliseconds are waited and then we apply the voltage again. If you think about it this way, look that if we talk about 3 milliseconds, here there are not 7. And in total, in a whole cycle, we have 20 milliseconds. According to the 3 plus 7 plus 3 plus 7, we have 20 milliseconds. These 20 milliseconds happen 50 times in a second. This is how the fan speed is regulated. If we wanted it to go slower, if we configure it at a slower speed, well, instead of waiting for 3 milliseconds to pass, it will wait for 7 milliseconds to pass. It will wait for 7. So, it will only apply this power to the fan. When it crosses zero, it cuts off. It waits for 7 milliseconds to arrive, and only 3 milliseconds of time are applied to it. It waits for it to cross zero, it disconnects. It waits 7 and at that moment it applies from when it crosses zero to wait 3 milliseconds, 5 or 7 milliseconds to turn back on and inject the electrons again. We need zero crossing detection because if not, there will be confusion between one side and the other of the electrons. It crosses zero, and when it activates, they are sent to one side only and then it is cut off. Then they are applied to the other side and then it is cut off. And then they are applied to the other side and then it is cut off. And the electrons go one way and come back, stop and come back. We do not vary the voltage, which remains the same, in this case, a peak voltage of 310. Nor do we vary the frequency, because we are not shrinking or moving away the electron sending. Respecting voltage and frequency, we can have a speed variation by sending less electrons. This is how the speed of an AC fan is regulated. These fans, of course, also need a capacitor to work. They are motors that we have already been analyzing, of alternating current of 220. We would not see the frequency or the voltage. Here are the coils. We will see all this, but we will go on to see it on the board. Please leave a comment if you have any questions.